Our topic is LR decay circuit over here. In this circuit, initially I have shown a circuit in which the inductor is connected, and from the inductor the current I0 is flowing at the shown instant, and at this instant I have shifted the switch from position 1 to position 2, and after switching the switch we will find out our circuit 2, and this is just after switching from position 1 to position 2, and at this moment current is I0 flowing, and that current I0 is also flowing through our resistor. Okay, now we will discuss, this is the condition t equals to 0. Now we will discuss this circuit at any time t. At any time t, here the inductor and the resistor is connected. This is circuit consideration at any time t. At this moment, let's say the current I is flowing through the inductor or through the circuit and resistor also. Now in the inductor there is an EMF which is E equals to minus L di by dt. Now I will write the Kirchhoff voltage law in the loop moving in clockwise sense. So minus L di by dt, and from here to here moving, that is minus IR, that is equals to 0, and from here we will get a differential equation which is di upon I, that is equals to minus of R by L dt. Now we will perform integration. At t equals to 0 the current is I0, at any time t the current is I. Now we will further solve this equation on integration ln I by I0 after substituting the limits, that is equals to minus RT by L, which will imply that the value of current I, that is equals to I0 e power minus RT by L. This current is found exponentially decreasing function as a function of time t. So when we will draw the function of the current with respect to time, at t equals to 0 the current is I0, and this current is exponentially decreasing, and after a long time current becomes 0. So this circuit is called as current decay circuit. Now here in the current the value I0 e power minus t upon L by R. Here L by R have the dimension of time which is called as time constant, and this is the time constant of decay circuit, and that is equals to L divided by R. This is our current decay circuit. Now if we analyze our differential equation, which is L di by dt plus IR, this equation is from here L di by dt plus IR, that is equals to 0. Then if we multiply this expression with current, then this comes up to be Li di by dt plus I square R, that is equals to 0. Now we will discuss these two quantities. At first we know that the energy of the inductor, that is equals to half Li square, and on differentiating with respect to time, du by dt of inductor, that is equals to L 1 by 2 into 2I di by dt. Now on solving this we will get du by dt of inductor, that is equals to Li di by dt. Okay, that means this term is our du by dt of inductor, and plus this term is the rate of heat dissipated in the resistor. Okay, now if we see that the value of du by dt of capacitor is equals to minus of dh by dt, this implies that the value of dh equals to du with minus sign, du of the inductor, and hence on integration delta h equals to minus of delta u of inductor. That means the heat dissipated in resistor, that is delta h equals to u initial of inductor minus u final of inductor. In LR decay circuit, the current finally becomes zero and the total energy of the inductor has been converted into heat.